Hi, I'm Dr. Incognito. In this video, we're going to discuss implicit differentiation. In a typical situation, we have y equals f of x, and we would like to find the derivative dy dx. In this situation, y is written explicitly as a function of x. However, for some very simple curves, it is not possible to express the curve y as a function of x, y as a function of x. As an example, consider the unit circle. The equation of this simple curve is x squared plus y squared equals 1. And in this situation, it is not possible to express the entire circle in the form y equals f of x. And this is clear because the graph of the unit circle does not pass the vertical line test. This is not the graph of a function. But it's still reasonable to ask what is the slope of the circle at a given point. So we want to know what is dy dx. The method for obtaining dy dx in a situation where we have an equation that describes a curve but not of the form y equals f of x, the method we're going to use is called implicit differentiation. And we'll consider two examples. One example will be to find dy dx for this unit circle. Another one is a curve called the folium of Descartes, which has the form x cubed plus y cubed equals 6xy, and the graph has a little loop in it here, a leaf, where it gets the name folium of Descartes. So this curve is not the graph of a function because, again, it does not pass the vertical line test. But we still want to know a formula for the slope of the tangent lines to this curve at any point. That would be, we want to know dy dx. So this is going to be a three-step process. In step one, we're actually going to assume that y is a function of x. And this runs contrary to exactly what I've just said. However, think about this. If you want to know the slope of a curve at a single point, let's say we want to know the slope of the circle at that point, then we actually don't need the entire circle. We would only need a little segment of the circle in order to figure out the slope at that point. And so if we only consider that little segment, it would actually be, y would actually be a function of x. So assume y is a function of x. This is true locally. It's not true for the entire curve, but it's true for small portions of the curve which are sufficient to tell us the slope at a given point. So after we assume y is a function of x, the next step is to take the derivative of both sides of the equation. So we'll take d over dx of both sides. And when we do step two, the expression dy dx will occur sometimes in more than one place. And that leads us to step three, which is to algebraically solve for the expression dy dx in the equation that results in step two. So let's see how this happens in each of these two situations. First, the unit circle. So the equation is x squared plus y squared equals 1. We will assume y is a function of x. There's no work to do there. We just keep that in mind for step two. So then we take the derivative of both sides with respect to x. The right side, the derivative of a constant, is 0. On the left side, we have the derivative of a sum, which is the sum of the derivatives. So the derivative of x squared with respect to x is 2x. And then we have the derivative with respect to x of y squared. And this is where things get interesting, because here y is a function of x. This is where step one is important. Y is considered as a function of x. And so what we have here with y squared is a composition. We have a composition. So in order to take the derivative of this composition, we're going to need the chain rule. Y is actually the inside of the composition, and the square function is the outside of the composition. In y squared, y is a function of x, which is inside of the squaring function. So we need the chain rule in order to figure out this derivative. The chain rule says do the derivative of the outside, that's the derivative of the squaring function. So you bring down the 2 and use the power rule like we did on x squared. Bring down the 2 and turn the power 2 into a 1, which I won't write as I did here with 2x. So that's the derivative of the outside times the derivative of the inside. The inside is y, its derivative is dy dx. It's that which we are searching for, dy dx. And that is equal to 0. So that is step 2. Then, as mentioned, when you're doing step 2, the symbol dy dx occurs. Here it occurs in one place. And step 3 is to algebraically solve for the symbol dy dx. So we can divide both sides of this equation by 2. So we have x plus y dy dx is equal to 0. And then we can solve for dy dx. We get y times dy dx is equal to negative x. And then dy dx is equal to negative x over y. So that will tell us the slope of a point on the unit circle. If you have a point x comma y on the unit circle, its slope, the slope of the tangent line is negative x over y. Okay, let's take a look at the folium of Descartes. The equation for the folium of Descartes was x cubed plus y cubed equals 6xy. So we assume that y is a function of x, and then we take the derivative of both sides. On the left side, it's very similar to what we had for the unit circle, x squared plus y squared. Here it's x cubed plus y cubed. The same ideas hold. The derivative of x cubed is 3x squared. And then the derivative of y cubed, that's a composition. The y function is inside of the cube function. So we do the derivative of the outside, that's 3y squared, times the derivative of the inside, that's dy dx. Now on the other side, this is a little more complicated than the last example. In the last example, the right side was a constant and its derivative was 0. Here, the right side is a product. We're going to think of this as a product. It's the function 6x times the function y. Because remember step 1, assume y is a function of x. So this is a product of two functions. If we want the derivative, we need to use the product rule. So the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. The second function is y. The derivative of the first is 6. So I'll write that as 6y. So this completes step 2, and we see the symbol dy dx has occurred, in fact, in 2 places. So altogether in this equation there are 4 terms. There's the 3x squared term, then there's the 3y squared times dy dx term, and on the other side we have 2 terms as well. 2 of the 4 terms have dy dx, and 2 of the 4 terms do not. We'll put the terms that have dy dx on the left side, and the terms that do not on the right side. So we have 3y squared times dy dx minus 6x times dy dx is equal to 6y minus 3x squared. I am algebraically here solving for dy dx. And to finish it off, we will factor dy dx out on the right side here. Dy dx times 3y squared minus 6x is equal to 6y minus 3x squared. And then we divide by the coefficient here of dy dx that you see in the parentheses, so that dy dx is equal to 6y minus 3x squared divided by 3y squared minus 6x. And generally speaking, that will be your answer. In this particular case, we could simplify a little bit. You could factor a 3 from the numerator and the denominator and write this as 2y minus x squared over y squared minus 2x. So there's a simplification that is possible here in this fraction. So there's a formula for the slope of the folium of Descartes, the slope of the tangent line at any point. If you have a point x comma y on this curve, if you have a point x comma y on the curve, then the slope of the tangent line is given by this formula here. Okay, so I'm going to wind up this video by doing two other very short examples, just partial examples. Suppose you're looking at an equation that involves an expression e to the y, where you're assuming y is a function of x. And then suppose you want to take the derivative with respect to x of that. Then this is a composition. This time the function y is inside of the exponential function, and so the derivative is the derivative of the outside. The derivative of the exponential function is itself times the derivative of the inside, which is dy dx. And one last mini example. Suppose we want the derivative of the sine of xy, where y again is a function of x. This is a composition where xy is inside of the sine function, so the derivative of the composition is the derivative of the outside times the derivative of the inside. And in this case, the derivative of the inside is a little bit complicated because this is itself xy, a product. It's x times a function of x. So we have to use the product rule in order to calculate this derivative. So we have the cosine of xy times the first times the derivative of the second plus the second times the derivative of the first. The derivative of x is 1, so I'm not going to write times 1. So the derivative with respect to x of the sine of xy would be the cosine of xy times the quantity x dy dx plus y. And then for practical purposes, if you wanted to work with this, you might want to distribute this cosine. So you would have x times the cosine of xy times dy dx as one term, and then plus y times the cosine of xy as the other term. You would do a step like this if you were trying to solve for dy dx. Okay, so there's a little bit of introduction to implicit differentiation. I hope you found this video helpful. Thank you for watching.